Hello everyone, this is Chandrasekhar welcoming you all once again to this Sunday Ka Funda series. As you all know, in this series we bring the most important concept of engineering subjects and try to make them simple, easier and interesting for you to understand through the live demonstration or the practical application. So in today's session, I will be talking about one of the important concepts of fluid mechanics. You just see the live demonstration and find out which concept is applied to these. So first of all, let us talk about the hand operated spray. You must have used or you must be using the sprays like deodorants or the perfumes. How the hand operated spray works. If you press this, then what is the concept through which the liquid comes out in the form of spray through the nozzle? Let us talk about the another experiment. If I take a piece of paper, ये paper मैंने लिया and because of the weight it is having a downward deflection because of the weight which is acting in downward direction. अगर मैं इसके ऊपर से air blow करूं, so what will happen? The paper should move further down or it should move in upward direction. Let us try to find it out. This is the piece of paper and if I blow air over the paper, oh my god, it is moving in upward direction, isn't it? Can you let me know what application or what concept it is applying? So let us move to the next experiment. So the next experiment is with the hair dryer. If I switch on the hair dryer and put a ball, ping pong ball over the hair dryer, what happens? Let us see. It is not falling down. If I further increase the speed, it is in equilibrium. Can you see? Let me take a bigger ball. I think the weight of the ball is smaller. Let us have a bigger ball and then do this. Why it is in balanced position? Can you let me know the concept behind this? Even if I slightly tilt this, still it is not falling down, isn't it? Let us move to the next experiment then. So guys, now there are two balloons which are separated by some distance, hanging balloons. If I blow some air between the balloons, what will happen? Let us find it out. They are coming closer to each other. Can you know? Can you find out what is the concept? Let us move to the next experiment. So guys, now I am again here with another setup. Let us try to find out how siphon works. There is a straw and I am putting it into the liquid like this. Now, can you see how it is working? So, what is the concept which is acting in all these experiments? Please write me in the comment section and let us try to find the concept, theoretical concept or the mathematics behind all these phenomena. Let us move to the theoretical part. Thank you. Hello everyone. Welcome back guys. So now let us try to understand the Bernoulli principle. The Bernoulli principle is very simple yet incredibly important principle in physics and engineering which can help us to understand a lot about the fluid flow. Bernoulli principle describes the relation between the fluid pressure, velocity and elevation of a flowing fluid which is having countless application, such as how the plane can generate the lift, how a liquid can drain out from the container. So this beautiful principle was first introduced by a Swiss mathematician and physicist Daniel Bernoulli in 1738. Let us try to understand the mathematical part of this Bernoulli principle. So the Bernoulli equation can be derived from the energy conservation as well as it can be derived from Newton's second law of motion. So according to this Bernoulli equation, the mathematical form, it says the sum of total energy of the flowing fluid remains constant. So as you can see on the screen, the first term in the mathematical expression represents the pressure energy of the fluid. The second term, V square by 2, represents the kinetic energy of the flowing fluid. And the third term, that is Gz, represents the potential energy of the flowing fluid. So the sum of these three energies, pressure energy, kinetic energy and potential energy for a flowing fluid always remains constant, and that is called as total hydraulic energy of the flowing fluid. So each term in this equation represents energy per unit mass. Each and every term represents energy per unit mass. The first term is pressure energy per unit mass for the flowing fluid. Second term, kinetic energy per unit mass. And the third term represents the potential energy per unit mass. So the only condition is when we do not consider the energy loss during the fluid flow, that type of flow is called as ideal flow. So we can say for an ideal flow, the total hydraulic energy or the total mechanical energy of the flowing fluid always remains constant. So the Bernoulli equation is the energy conservation equation for an ideal flow. Alright. So if we multiply this whole equation, this is the energy form of Bernoulli equation. If we multiply this equation with rho, rho is the density of the fluid. So the left hand side will become, the right hand side will become constant. Constant multiplied by rho. Rho is a constant parameter for incompressible fluid. So that will give rise to the pressure form of the Bernoulli equation. The first term P represents the static pressure of the flowing fluid. The second term rho V square by 2 becomes the dynamic pressure of the flowing fluid, which is the pressure which is developed due to the velocity or the kinetic energy or the motion of the flowing fluid, which depends on the density as well as the velocity. And the third term represents the hydrostatic pressure of the flowing fluid. It is the pressure which is exerted due to gravity. So the sum of these three pressures remains constant for an ideal flow. So now if we find out the unit of each and every term in terms of energy, then each and every parameter in this equation represents energy per unit volume of the flowing fluid. And energy per unit volume is nothing but Newton per meter square or Pascal, right? Now, if we multiply this equation with rho and g, both are constant parameters, so the right hand side will become constant. So the third way of representing the Bernoulli equation, that is called as head form of Bernoulli equation. So what we get, the first term will become P by rho g, that is the static pressure head of the flowing fluid, which can be absolute, which can be gauge. The second term represents V square by 2g, represents the velocity head, or we can call it as kinetic energy head, or it can be called as dynamic pressure head of the flowing fluid. And the third term represents the static head, or we can also call it as the datum or the elevation head, or the potential energy head of the flowing fluid. So Z is the depth or height of the point from a reference line. So summation of these three terms will make the total energy head of the flowing fluid H, which remains constant for an ideal flow. So there are three types of expression. If we write this expression in terms of energy, so unit of each and every term, or each and every term represents energy per unit weight of the flowing fluid. And energy per unit weight becomes the meter. That is why it is called as head form of the Bernoulli equation. So if I summarize all the three forms of Bernoulli equation, the various form of Bernoulli equation can be written in terms of energy form, in terms of pressure form, as well as in terms of head form. But the most important thing is the Bernoulli equation cannot be applied everywhere in the fluid flow. There are some limitations, there are some constraints, there are some assumptions to apply the Bernoulli equation. We need to understand the significance of these assumptions before applying this Bernoulli equation to the fluid flow. The first and the very, very important assumption is the flow should be non-viscous or inviscid flow or frictionless flow. It means that the friction due to, or the frictional energy loss due to viscosity of the fluid is negligible. It must be zero. The second assumption is during the fluid flow, the flow behavior should not change with time, or we can say the flow must be steady flow. The third assumption says during the flow, the density of the flowing fluid should remain constant. It should neither vary with space nor with time. That means the flow has to be incompressible. Another assumption, because it is an energy conservation equation, so there is no transfer of energy from outside to the fluid or from fluid to the outside. There should not be any form of energy transfer, neither in the form of heat nor in the form of work. All right. And the last and the again very, very important assumption is the Bernoulli equation is applied to the flowing fluid along the stream line, along the flow only. All right. So let us try to apply this Bernoulli equation in a mathematical equation or mathematical problem. For an example, if there is an ideal flow, it means there is no energy loss during the flowing fluid due to friction. The frictional loss is ignored, negligible. So if the fluid is flowing from inlet 1 to outlet 2, at inlet 1, the potential energy is, this is the reference line, let us say, the height of the point 1 is the potential energy head Z1, and there is a outlet point 2, the height of point 2 from the reference line is the potential energy head Z2. V1 is the velocity of the flow at the inlet 1, and P1 is the static pressure of the fluid at 1. Similarly, P2 is the static pressure at point 2 outlet, and V2 is the velocity of the flowing fluid at section 2. If we apply the Bernoulli equation between 1 and 2, the total energy of the flowing fluid at section 1 will remain same as the total energy of the fluid at section 2. If we write this equation in head form, so we can write the static pressure head plus the kinetic energy head plus the potential energy head at the inlet 1 will be equal to the sum of pressure energy head, kinetic energy head, and the potential energy head at the outlet. All right. But if the flowing fluid is not ideal, if the energy losses are taken into consideration, for real flow, there are always energy losses taking place. So in that case, we cannot use the Bernoulli equation, but yes, the energy conservation equation can be applied because energy conservation is universal law. So the Bernoulli equation with slight modifications can be written for real flow taking place from the inlet 1 to outlet 2. So what we can say, in the direction of the flow, the energy of the fluid, total energy of the fluid always decrease. So the energy conservation equation can be written as total energy at the inlet is equal to sum of energy at outlet plus the energy loss from inlet to outlet, that is due to friction mainly. So if we write this expression in the form of head, then we will get the sum of potential energy head, pressure energy head and the kinetic energy head at inlet will be equal to the sum of pressure energy head, potential energy head and kinetic energy head along with the head loss due to friction. That will be the term on the right hand side, right? Because the flow always takes place in the direction of decreasing total hydraulic energy of the fluid, or we can say a fluid flow, or we can say the fluid always flow in the direction of decreasing hydraulic energy, or in the direction of the fluid flow the total hydraulic energy of the fluid always decrease. All right, so let us see how the Bernoulli principle or the Bernoulli equation is applied to the practical examples, to the practical situations. For an example, there is a horizontal pipe in which the ideal fluid is flowing, right? If the fluid is moving through a converging section of the pipe, in the converging section, what will happen? The area of the flow will reduce, and due to reduction in area of the flow, the kinetic energy or the velocity of the fluid will increase according to mass conservation. According to continuity equation, that is mass conservation. Mass conservation. And when the kinetic energy of the flowing fluid increases, so definitely the pressure energy of the fluid must reduce in the flow direction due to Bernoulli principle. This is called as Bernoulli principle. If the kinetic energy increases, so pressure will decrease. That is actually happen in nozzle. There is an increase in kinetic energy. That is why there is a decrease in the pressure energy of the fluid. Now, when the fluid flow is taking place in the diverging section of the pipe, so during in the diverging section, the area of the flow will increase, and due to increase in area, the kinetic energy or the velocity of the fluid will decrease in the direction of the flow, that is the mass conservation. And now if we talk about the energy conservation or the Bernoulli principle, we can say due to decrease in kinetic energy of the fluid, there has to be an increase in the pressure energy, because the total hydraulic energy for the flowing fluid always remains constant. So these are the Bernoulli principle. This is called as Bernoulli principle. We can apply this Bernoulli principle in many real life problems to analyze the real life situations, which I have showed in the previous part of this session. For an example, in an hand operated spray, if you push the plunger, the air velocity gets increased, and due to increase in the velocity of air, there is a decrease in the air pressure, and due to low air pressure near the nozzle, the liquid from the bottle will rise through the metal tube up to the tip of the nozzle from high pressure to low pressure, and due to the force exerted on the plunger, the liquid will get scattered and it will come out in the form of spray. That is how the hand operated spray works. Similarly, the aeroplane wings are designed in such a way that the shape of those wings are aerofoil, and in case of aerofoil, the fluid, the air which is flowing over the aerofoil is moving with a higher velocity, so it is having low pressure, and the fluid which is moving below the aerofoil will be at a lower velocity, it is having the high pressure. Due to the pressure difference, there will be a force exerted from high pressure to low pressure from the bottom towards top, so the lift force is developed due to the difference in the pressure. Similarly, if we talk about a ping pong ball, how it get balanced. So the air near the ping pong ball is having higher velocity because of this hair dryer. So the higher velocity implies low pressure of air at the region. But away from the ball, the fluid is having low velocity. So that means the air is having high pressure. So from high pressure to low pressure, there is a force exerted towards inward direction on the ping pong ball. That is why the ping pong ball is balanced due to the pressure force exerted from outside towards inside on the ping pong ball. We can have a look to a couple of more examples which uses the concept of Bernoulli principle. During the high winds, the velocity of air is very high and the pressure of air becomes very low. But inside the room, inside the hut, the velocity of air is low or negligible. So the air pressure is high. So during the high winds blowing over the roof of the hut, there is an upward force developed due to the pressure difference, that is the lift, and the roof is always lifted in upward direction. And very simple example we can have a look. When we blow air on the paper, when we blow air, there is a high velocity due to which there is a low pressure, Bernoulli principle, and the pressure below is high because the velocity is low. So the paper will get folded in upward direction due to the force exerted from high pressure to the low pressure. It will not get folded in downward direction. Similarly, I have already shown you the balloon. If you blow air between the balloons, the velocity of air is high, so the pressure is low. But the outside these two balloons, the air pressure is high because of low velocity. So there is an inward force exerted, and by blowing the air between the balloons, the balloon will always try to come closer with each other rather than going away. All right. So I hope you guys have understood and you guys have got the feel of the various unlimited vast applications of Bernoulli equation. That is all from my side. See you in the next such video. Thank you guys. Thank you. Take care.